Okay, so this is the first of our videos on the Euclidean algorithm. That's why it says part 1 here. These are broken up into two general categories. One, because these are the two main things we want to do with the Euclidean algorithm, is find the GCD of two numbers, two positive integers, this a, b, and z plus. And the other one is find modular inverses. If the GCD of two positive integers is 1, we can find the modular inverse. And this is a big thing that comes up in a lot of problems. When is there a modular inverse? We use it in proofs. Knowing that there's a modular inverse is one of the steps in the proof. And maybe in a problem, we actually need to find the modular inverse. So it's going to be two sort of categories of videos. And this one is the one where we're going to use the extended Euclidean algorithm, actually, which is maybe the one they saw in class, showed you in class, which no one really ever understands. When I took number theory for the first time many years ago, I didn't really understand it. In order to really understand it, it actually turns out that the process, the sort of short, quicker version that we're going to use to actually compute a GCD, if that's all we want to do is find the GCD, that process and why it works is kind of related to this, and of course it's related, but it's kind of the key to understanding this and why it works. So we're going to start with this one. In this video, we're going to do this one. We're going to find the GCD of two numbers. And by the way, if all you wanted from this video, the reason you clicked on this video was that you want to find the GCD of two numbers, let's just do that now, because people are probably like, why are you rambling about this? Just show me how to compute the GCD. We'll do that. We'll get that out of the way. Then we'll talk about why this worked. I'll show you what to do. Then we'll see why it worked and start to use it to understand some deeper stuff, which will help us with things like modular inverses. Okay, so suppose I want to find the GCD of 80 and 15. Well, this is the technique for this is I'm going to subtract the 15 from the 80. The GCD of 80 and 15 is actually going to be the GCD of 80 minus 15 and also 15. And my battery is low. I think we'll make it through the end of the video though. That's okay. And what's the GCD of 80 minus 15 and 15? This is GCD of, I think that's 65 and 15. I think 80 minus 15 is 65. And then I can subtract again. So we subtracted the lower number from the large number, the smaller number from the larger number. We can do that again. This is the GCD of, I think it's going to be 40 and 15, and we'll subtract it again. This is the GCD of 25 and 15, which is the GCD of 10 and 15. And now there's been a switch. That's not where I wanted to do it. There we go. 40, 25. There's been a switch now. The 10 is the smaller number. Up until now, 15 has been the smaller number. Now we have one which is smaller than 15. So we will subtract this is the GCD of 10, and we'll subtract 10 from 15. It's 5. Now 5 is the smaller number. And then we'll subtract, this is the GCD, we'll subtract the 5 from the 10. It's now 5 and 5. And so they're both the smaller number and the larger number. They're equal. And so 5 is the GCD. 5 is the GCD of 80 and 15. And if we want, and this is one of those things which will help us sort of understand what's going on with the Euclidean algorithm. So this isn't the Euclidean algorithm, right? By the way, this isn't sort of the same idea, the same principle that we use. The idea behind the Euclidean algorithm used sort of more quickly because using the Euclidean algorithm, actually using it to find the GCD is not very efficient. But using it to find modular inverses, you actually need the slower, sort of more cumbersome version, the extended Euclidean algorithm, if you want to actually compute the modular inverses. All you want is the GCD. You want to use this one. The next step, so at this point, I know the GCD is 5. If I went one more step, then you would subtract 5 from 5. This would be the GCD of 5 and 0. 5 and 0. And this is not really making a lot of sense here. Or I mean, it kind of is, because every positive number, every number divides 0, and the divisors of 5 and 1 are 5, or the divisors of 5 are 5 and 1. So technically, we would be able to see that 5 is the GCD of 5 and 0. The point of putting this in, though, is to understand that there's going to be a step in the Euclidean algorithm, the big Euclidean algorithm, where you hit a 0 and then you stop and you go back to the previous step. And the last number that you had, the last non-zero number here, 5, would be the GCD. So this was how to do it. This is the sort of computational thing. If I want to find the GCD of 80 and 5, I can just do this. I can keep, or 80 and 15, I can just keep subtracting the smaller number from the larger number, and you don't even need to write the GCD. every time you can just put brackets. You can put the 80 and the 15 in brackets, and then just keep replacing the smaller one with the, or the larger one with the larger one minus the smaller one until they're equal, and that's a GCD. But you might have noticed that so doing this, subtracting 15 repeatedly one at a time doesn't make a lot of sense, right? I could have skipped this. I could have done these subtractions all at once. I could have subtracted any multiple of 15 from 80. It's actually true that that the GCD of 80 and 15 is going to be the same as the GCD of 80 minus any multiple of 15. And this is the idea behind the Euclidean algorithm, the big one, which is that the GCD of these two numbers is going to be the same as the GCD of this other pair of numbers, which are then smaller, and then we do this repeatedly until we sort of run out of space. It's called the well-ordering principle, and we get the GCD. But if I take a multiple of 15, which is less than 80, like say, I don't know, 15 times 3, which is 45, this would be the same as the GCD of 80 minus 45 and 15, which is the GCD of, I think this is 35 and 15. We could do that. But why? And then this skips us down a lot in the process. What if though, I just noticed that I could do this in one step by noticing that 80 is equal to 75 plus 5, which is 15 times 5 plus 5. So this is actually, in this case, what we're doing is replacing 80 with 80 minus 75, and that's 15, and this is 5 and 15. So I've actually replaced 80 with 80 mod 15. So the GCD, what we're saying is that the GCD of 80 and 15 is the GCD of 80 mod 15, so the remainder that 80 leaves when we divide by 15, and 15, and then it goes much more quickly, right? We're going to get to the GCD much faster if because this is basically when we replaced 80 with 80 mod 15. What we were doing was we were replacing 80 with the largest multiple of 15, which was less than 80, right? 80 minus 5 times 15 is equal to 5, and we replaced the 80 with, it's up here, I'll double highlight there. We replaced 80 with 80 minus the largest multiple of 15 that was less than 80. So that's the remainder that we get when we divide 80 by 15. And so this is the underlying principle, which is that the GCD, this is why this was working, is the fact, and we'll talk about why this is true in the next video, the fact that the GCD of A and B, any two numbers, is actually the GCD of A and B plus A times, say, K, where K is in the integers. This is the principle behind this. And this is the general idea behind why the Euclidean algorithm, the big Euclidean algorithm, is going to work. And so this is the technique, this is the tool that we use if we actually just want to find a GCD. So hopefully people are happy with this. In the next video, we'll see why this is true. We'll prove that this is true, and then see how we can use this to develop the Euclidean algorithm and how we can use that to find modular inverses and figure out when there are modular inverses. That's going to be the second part of this. This is not the order that it's normally done in, right? Usually in a number theory course, they'll just show you the Euclidean algorithm. You don't really understand why it works, and it's confusing, and there's P's and Q's and indices all over the place, and it kind of hurts your brain. And it's hard to use, and it's really sort of unpleasant. This is a quicker, easier to use version of it, which I think is well, I'm almost out of battery. I'm gonna have to wrap this up. Getting to the hang of this not only allows you to actually compute GCDs quickly and efficiently, which is really nice. And we should actually, if I had more time, would have done a bigger example. We can do a bigger example in another video. But the idea is that thinking about why this works, and this is the key to getting really, really good at math, is thinking, why does this work? What is the idea behind it? Understanding that idea, then coming back up to the harder one and thinking, okay, now that I understand the concept behind it, how can I figure out why this is working and learn how to use this? Because we actually do. This one will do it if we want to just find a GCD, but this one, if we want to find modular inverses, we're actually going to need the extended Euclidean algorithm, which is much easier to use if we actually understand it. A lot easier to use if we actually understand it. And this is the key to that. And so hopefully this I sort of convinced you that this is legitimate and maybe piqued your interest in this by showing you actually how to compute GCDs quickly and efficiently.